Make48 is funded by
Stanley Black & Decker provides tools and services around the globe to help turn great ideas into reality and to help us shape the world we live in. We proudly support programming that inspires invention, innovation, and hard work. Together with Make48, we're providing men and women the tools and resources to build a better world. Stanley Black & Decker, for those who make the world.
On the last Make48, Rich sought out Travis's advice on the Nary.
There's a whole lot of stuff that needs to get inside of this thing.
And Bob spoke with the guys at Machine Head.
This is where we started, and then this is kind of what we came up with.
Big difference.
Now the prototyping begins.
Having IP on your invention, on your product, whether it's patent pending, a utility patent, design patent, trademark, is really, really important, especially with products like these three. They could very well go to bigger companies. If you haven't got your ducks in a row and all that secured or in motion, a company will often just decline you straight away. This is the initial design that it had coming out of the competition itself. It's going through many other variations right now. By the shape of what you see, is this another design patent? Or is there something else that we could do this, depending on what we add to it for protection?
The design patent can only cover the ornamental appearance of an object. And one of the ways I explain design patents to people a lot of times is silverware, like a unique style. Like when we registered and got married for our silverware pattern, there was 20 different patterns. A fork's not new, so you can't get a utility protection on the fork itself. But all of those different patterns clearly had different looks to them. So those patterns were protectable by design patent. In this particular case, we have something here that has a function. So to the extent that it has a function and the function is new and not, how it does or performs the function is new and not obvious, we could be able to get utility protection. It's really hard to get utility protection on I don't want to call it a simple item, but items that don't have a lot of things there, especially no moving parts. So it just makes it hard, not because it's not new, but because it may be an obvious combination of other things. So when we're looking at this, you know, it has a function. You slide it under the door and turn it to lock the door from moving against the door jamb. So it does have a function. So the problem with the design patent aspect would be if we're trying to get the shape, the bends and how long it is and all the different bends are probably dictated by the function that it's going to perform. So it has these bends because you want it to wrap around the door, or it has to be flat here so it can all slide under the door. All of those shapes actually do have a function, so it may make it difficult. Now, that being said, this handle certainly doesn't have to be that shape. So that handle, you know, if you were doing a design patent, you might show this part in solid lines, show all of this in dashed lines, just to kind of give you an idea of where what the handle is used with. But that's not part of our claim of the design. And then this particular shape of the handle could be protected, again, if it's a new and non-obvious shape.
There are two improvements we're working on. The handle has been one of them. We're trying to make sure that a 5-year-old or a 6-year-old can use this device, and they might not have the strength in their arm. So to have a flat back on here where they use their feet or their foot to press down, that's one thing. Also, the variations of doors. There's over 30 variations of left to right combinations of doors out there that this product must fit. This clearly can only probably do 1 or 2. So the new adapter can be adapted to here and can be modified to suit that door. Is that something you think could be protected? Is the plastic component that goes on here?
Yeah, so once you've added that, the more parts you're going to have, the more functionality that those parts allow it to do, the interplay between those, the more likely it is you've got something that's not only new, but now it becomes non-obvious.
Bob's also working on some different fixtures and attachments that will go with it. That may allow us to do patent pending and utility patent.
The adapter, however it is, if it's a way that you're figuring out how to make it work with these different doors, and it provides its own unique functionality to make something that otherwise would work with 2 doors now work with 30 doors, then obviously that's going to be key. And in fact, that'll be not for the utility aspect, but that'll be key to making this a viable product that lots of people can use. What you would want to protect so that the competitor, someone coming along trying to make this, they would need something like that too, otherwise their product's only going to work with 2 door types as well.
Putting a patent on a product, it's not the product in general, it's often a feature of a product, correct, that the patent is actually on.
Well, and that's because a lot of times it's the feature that makes it newer and better than what's been done before.
It's a better mousetrap.
It's a better mousetrap.
One of the things I did was I went to the hardware store and picked up a pack of 2 carbon monoxide detectors and opened that up, got those electronics out, and realized, okay, they're never gonna fit in that size bird that the school kids made. It's just not gonna fit in there. So what I did was scale that up and printed a larger bird, and it was just too big. It's not attractive at all. But it scaled it up and made it work, but it's not gonna be something people would wanna buy. Not like that. Another thing that came up about the Nary when I was talking to the team was making it battery operated. I'm gonna call Rick Keller, a good friend of mine, who also happens to be a tool tech, and he is an engineer that knows more about batteries than anybody I've ever met. So he is gonna, I'm sure, be happy to come to the shop and help out with the batteries. The reason I asked you here today is to get your thoughts on the Nary. So back from Baltimore at our last competition. The Nary was by the Chicago Art Institute students, portable carbon monoxide detector. Yeah. And what this does, somebody would, when they're traveling, going maybe staying in a bed and breakfast or a share space, maybe a loft or some older apartment that doesn't have modern electronics in it, the Nary would detect carbon monoxide. One of the thoughts we've had through the process of trying to develop this, get it into more of a working prototype, is what would happen if we made this rechargeable, made the batteries rechargeable.
Sure.
You're the best battery guy I know in the world, and that's why we brought you here, to talk to you a little bit about batteries and see what your thoughts are on making this thing operate by battery. So that way when people are, by rechargeable battery, that way when people are traveling and that sort of thing, they don't have to worry about trying to find a AA battery. Oh, my Nary's not working, let's go find a battery, let's go find a convenience store.
Sure.
You just plug it in like you do your cell phone, same kind of thing, charges up and lasts for maybe a couple nights or so at least, I would think.
Yeah.
But what's your thoughts on that? So tell me what you think.
Yeah, well, the good news is with the battery technology ever increasing and getting better and better every day, new technology is coming out all the time. I think there's absolutely a perfect battery solution for this application. A little bit about batteries. You can choose to design one that's custom, specifically made just for this application that would take into account, the amount of power required from the electronics to last you a given period of time. Whatever we set the requirement for that to be, and then that will help dictate or help determine the size of the battery needed. I brought a couple of different battery samples with us today, just to kind of give you a feel for some of the different sizes, some of the different capabilities and capacities of batteries, and some of the different battery technologies. There's some existing technologies that have been around for a number of years, a few decades in fact, and those are all readily available. Everybody's very familiar with those. Just quickly, I'll point out this is a AAA standard alkaline battery. Everybody's very familiar with these. You could buy them at literally any place you probably walk into today. You could probably buy this. The good part about a battery like that is that it is readily available, and because it's made at such an incredibly high mass volume, it's incredibly inexpensive for what it is.
Not rechargeable.
It's not rechargeable, so that's what we call a primary battery.
Okay.
There's several different shapes and sizes and capacities of primary batteries, but they're not rechargeable, so they wouldn't be good, in at least my opinion, in this type of application. The possibility of this concept being a reality 10 years ago, 20 years ago, especially 30 years ago, really wouldn't have worked at all. And that's because, at least in my opinion, the technology that was available then wouldn't have supported it. So nowadays, as electronics get a lot smaller, you can fit them into products like this. Different battery technologies offer different, what we call energy density. So how much power can I put into how small of a product or how small of a part? And different battery technologies offer different advantages of that. The new kit on the market is lithium ion or lithium polymer. There's different slight differences in technology and terminology with today's battery technology, that it's much more stable, much more secure, much more reliable, and the benefit much smaller. So I might be able to get by with a little battery like this guy.
That's what I'm talking about. Yeah.
This is a 25 milliamp hour battery, which may not mean a whole lot to a lot of people, but it means it can power a certain amount of electronics for a certain period of time without needing to be recharged. And this is completely rechargeable. This is a lithium ion battery. It's very small. It's made for a very small piece of electronics. But this is made to be embedded into the electronics. And basically you have a small port that is exposed on the outside. So if something like this was embedded in your product or in the product, so it could be in the product, and then you would have a small port that would be exposed to the outside world. There is a small amount of electronics that would be required to successfully charge the batteries, and they can be easily incorporated into the electronics that's controlling your product. So your NARI is a carbon monoxide detector. So we isolate a small amount of real estate on the electronics that are in the bird or in the device for control technology, and then literally all we have is just a simple USB connector on the outside world.
So you could put this directly onto a circuit board, correct?
We could put those electronics, the monitoring electronics, right on the circuit board, or maybe a secondary board, a daughter board, whatever, right on the electronics. And it doesn't require a tremendous amount of real estate space. A really small PCB board, not much bigger than this battery, in fact, could easily control all the electronics for that battery. So it doesn't take up a lot of space, and it keeps your product and your battery operating safely and smoothly for the life of the product, literally. If you chose not to want to have a cable plug in your device, they make inductive charging. And the way that works is you have your battery pack inside of your device, you have a small inductive pad that's also embedded into the device, and you literally set it on what we'll call affectionately the nest. And so the bird can sit on the nest and it can charge via inductive charging.
Yeah, but would that increase the electronics that go inside of the bird? Maybe with a coil of wire or something that's required to pick up that inductive charge?
Not necessarily. So for example, maybe you have one at home, I do myself, I have a toothbrush that works on inductive charging, electric toothbrush. And the base on it's really small. It's actually probably smaller than this. And it sets on a very, very small pedestal and does inductive charges just fine. We would want the battery to be as small as what we can and as light as what we can, so it doesn't become cumbersome or burdensome to carry this thing around with you. It's portable, right? It's supposed to be a portable product. For this application, I think a standard, what they call a prismatic cell, it's a flat lithium ion cell, would be absolutely perfect. We can tuck it right in with the electronics. It doesn't take up a lot of extra space. The amount of electronics required to allow the battery pack to operate in a normal, safe environment, it would be very, very nominal, very small. We could easily incorporate that into possibly even the same PCB as the electronics that are used to monitor for carbon monoxide.
So every time I talk to you, I learn more and more about batteries. It's just so much. There's so much new stuff happening in that world, which is great, and I'm real happy that you came by today. Just stopped by, gave me a lot to think about. We found out that, yeah, the batteries, no problem. So we can get those down to the size they need to be. They'll fit inside that smaller bird, no problem.
Work continues on the flat light. Stan begins testing different techniques to bring his version of the prototype to life.
The first thing I wanted to try was mirrored acrylic, and I thought, well, if I can bounce the light around inside, you know, like a light sandwich, you know, and scatter it out sideways. It did work to a certain degree, but it was so diffused that I think we lost the ability to cast light very far. It was more of a diffusion process. And acrylic optically is, you know, may not have been a good choice for this. So I thought maybe polycarbonate would be the next choice. Acrylic has a really good conductive quality for light. It passes very much like a straight line through acrylic. The disadvantages are that it's fragile, it will turn yellow over time due to ultraviolet light and things like that. It's very hard to make a whole product that can be fragile this way with acrylic. Polycarbonate is extremely tough material, has a lot of really good refractive qualities through it. So light tends to bend through it, so they use it in a lot of lenses as like such. But light also is resisted as it comes through, so you gotta know how much to use when you're trying to gather as much light as possible and pass it through. So keeping with the idea that I wanted it flat, kind of like a coffee coaster that would accommodate all or most flashlights. I went to the polycarbonate and we used 1/8 inch and we tried to heat form it and tried different techniques to shoot light through it, and I found that the light losses were too great and it was too thin. So I thought the next best thing would be some kind of reflective process and some kind of lensing at the edge to culminate the light. The next step was to just start hacking away at aluminum on a lathe and a milling machine and polishing it. I've made reflector systems before with aluminum. It polishes up very nicely. So I did several different experiments with first drawing up a vague geometry in Rhino, which is a 3D kind of modeling program. And then from that basic plan, kind of start building test models on the lathe. Testing materials against the real world is the most important thing that you'll do in a product design, because you can live inside a computer model and it is not going to completely represent reality. So trying several things, trying the acrylic, trying the polycarbonate, and then ultimately using polycarbonate as an end lens and a reflective surface inside was the thing that passed the test the best. But until you actually try a product, even if it's crude, you're not going to know anything. Well, there was a lot of repeat processes when I was on the lathe, and I had to dial in the correct angles to reflect the light because I wanted to make sure the hot spot that hits the lens was in the right place. And then when I felt that the angles, the incident angles bouncing through this object was hitting the lens at the right place, putting it on the shop floor and testing it for the first time was very fulfilling. I was just like, oh my God, it works.
After making this giant bird, this big old turkey, and realizing that's not gonna work, that'll never sell. It's clearly not what the team had in mind when they invented this thing. So the next option is to keep the small size of the bird and rebuild the circuit board. So rebuilding a circuit board for a carbon monoxide detector is a little bit more complicated than, let's say, rebuilding one for a flashlight or something like that. First thing I want to do is talk to some people who build boards, and we know some folks over at Digitron. That's what they do. They make printed circuit boards, and I think that'd be a good place to start.
That's what I want to talk to you guys about. How do we get this shrunk down enough to go inside of that?
Right. So, we have a lot of engineering resources to be able to handle these things. So we take on these types of projects all the time. We have a lot of people come in with proof of concepts that we need to take and turn into a real product. So in this case, if we were looking at this project, if we were taking here, just this board here, we would look at shrinking this down. And nowadays, these components are real big, but with the cell phone markets, all these components are micro small now. So we would be able to reduce this board down.
So they were using larger than what you needed to on
Yep.
here? Okay.
Yep. Which is okay. You design to where you're going in the end. But now that we have to miniaturize it, we look at it, and maybe you look at this and say we don't need an LCD or display on it. You're probably going to want some buttons to turn it on and off, and how you're going to get power to it. This has got a battery in here. Yeah. Are you going to have a battery pack that you have to plug into the wall? Is it going to be rechargeable? There's a lot of different things you have to think about when you're powering the unit. And what happens if there's no power, right?
Yeah, I think battery is the way we'd go on this, possibly rechargeable.
Yeah, so then, rechargeable, then you got to monitor the battery and make sure that, if the battery's low, then it's going to give you an alarm. So there's lots of things that you think about it when you're powering a unit that you may not worry about until you actually get it out in the field and you start thinking, oh, there's some other use case scenarios for here that I have to think all the way through.
Especially being a life safety item like that, you want to know if that battery's low. It's not like a flashlight or something. So
Exactly.
yeah.
That may be one of the things that's a little bit different for being a portable device like this versus something that's normally mounted in your home, is we need to think through those use cases, and power management is an important part. You know, having a chirp that happens once every 5 minutes, as annoying as that is in the middle of the night, may not be adequate for something that's a portable product that you're using, you know, by your bedside. And like you say, how to manage the turning it on, and do I know that it's on, and maybe some positive feedback that it's powered up and ready to go, the battery's in good shape. You know, maybe there's some things that we need to think about that differentiates the Canary from one of these standard products that you would mount to the ceiling.
Yeah, that's true.
Yeah, a lot of times you just worry about what the core function is, but there's a lot of things around it that you have to worry about.
Would that be something that maybe UL would come in on, or?
They would help you with that. Yep.
Okay, and they have requirements, I assume,
Yep.
with these.
And we're used to design into those requirements.
Okay.
So you look at the classification it goes into, and then we would design to those classifications.
Okay. Yeah, that makes sense. So there's a lot more involved than just a simple electronic device that's not trying to save someone's life necessarily.
Yeah, there's a lot of those subtleties that we really need to think through up front, you know, and then you go through the use cases, and all right, let's simulate the use. Let's get a focus group. Let's walk through the scenario of, you know, the Airbnb, the old home, taking it to grandma's house, you know, all the different things that would come in, and line out those use cases and make sure that, all right, well, the batteries went dead and nobody knew it. So how do we address that issue? I thought it was turned on, but it wasn't. How do we address that issue? And those are some of the upfront things that we need to think through.
Yeah, I see. So what we're talking about, it sounds like a long process.
It can be.
Yeah, so how long exactly are we looking at here to do something like, to design for the engineering side of this?
Yeah, on this particular one, we'd start with the schematic, and then that schematic goes into what we call the printed circuit board assembly, which is this green board, and then that part goes into the final assembly.
Okay.
So then you have 3 distinct phases. You got the mechanical 3D modeling part, you got the circuit board assembly, and then you have software that gets written and loaded on here, so you have to worry about those as different phases in your project.
Okay.
So the circuit board phase could take, for a project like this, you know, a couple months. The software, probably 6 to 8 weeks, and then the solid modeling, you know, possibly another 4 to 6 weeks. So when you add up that timeline and the cost of that, it adds up.
Yeah.
And then that's to kind of get your first iteration. And then you got to send it out, get it tested like Brian was referring to. You got to go out and get your use cases, get it out in the field, test it, and then you come back and refine it, and you kind of do that process again. Much shorter process the second time around, because you're just refining the design at that point.
Of course, I'm a geek for factories. I love just seeing how things are made. I could spend days and days in them. So I love robotics, pick and place machines, and just seeing how circuit boards are made is fascinating. With Digitron, you know, they're heavy in automation. They have the pick and place machines that are basically robots that pick up and put the parts where they need to go, and then they roll the boards through ovens and solder them in place, all automated.
From a mechanical standpoint, you know, the other thing is we talk about the solid modeling and the mechanical design. It's never too early to start looking at the design for manufacturing side of the mechanics as well. You know, if this is going to end up being an injection molded part, we need to think about, okay, where's the parting line going to be? How can I separate this tool without a lot of extra expense and efficiencies in that side of things too? So that needs to start early as well. So we've got several weeks that go into all right, let's look at shapes, let's look at sizes, let's do that. But then let's also start talking about, you know, how are we going to separate the two halves? Where's the circuit board going to go? And then at the point we go through probably several iterations of 3D printed models, we'd eventually go to an injection molded tool part, which, you know, once that design's done, you've probably got about 3 months worth of tooling time, and then test shots and then adjustments, and make sure it fits together well, make sure the texture is what you need and the sound comes out. And, you know, there's with a piezo like that, there's some resonance qualities that we want to make sure we get out.
So we're talking overall, you're looking, I'd say at least a year, right?
I mean, if you look at going through all those cycles and all those processes, going out and getting your use case studies and testing it, validating, you know, you got to make sure that, you know, when you hold it and you drop it on the floor, you know, you got to make sure that it's going to be able to withstand that. So there's drop tests that you got to go through. So it could take up to a year for sure.
So the good thing about Digitron going there, well, other than getting to see that cool factory, is they said, yeah, no problem. They looked at the board, they looked at what we needed to have done. I said, that can definitely a doable thing. No problem about it. But we're looking at about 12 to 18 months engineering time and testing. It's a long time-consuming process. We didn't get into money, but engineering time for 12 to 18 months, you can imagine it's probably going to get pretty costly.
On the next Make48, we travel to the teams to show them the refined prototypes.
When we left last time at the event, last time I saw you guys, you gave us one of these.
And get their feedback on the progress so far.
Is this plastic?
Yep, we 3D printed it and then use Carbondo.
Make48 is funded by
Stanley Black & Decker provides tools and services around the globe to help turn great ideas into reality and to help us shape the world we live in. We proudly support programming that inspires invention, innovation, and hard work. Together with Make48, we're providing men and women the tools and resources to build a better world. Stanley Black & Decker, for those who make the world.
To learn more about the invention process and to get to know the teams, visit Make48.com.